all good over there? So, one of the things that was brought up to me earlier today and yesterday was, when do you use which thing to do which calculation? And it was asked in several different methods, but it was basically the same thing. Like, I don't know when I should use this way of finding the field versus that way of finding the potential versus this way of finding. And I can understand that idea. What's concerning to me is there isn't a right way to do it. You can choose any number of ways to do any of these problems. The point is that you should choose the one that I think is the most efficient, but you should probably also choose the one that you know how to do. Now, it is true that some of our examples are definitely easier to work one way versus another. That should be clear. But there are clear situations in which there is only one or two options in doing a problem. So I want to go back to the one that you were presented with on Friday for just a minute to talk about how you could have approached it. And that's not a single idea, that there's multiple ways you could have approached it. But there are certainly ways you could not have approached it, things that would not have worked regardless. So let's consider the situation from Friday, just to get us started. So we had a ring of charge, total charge Q, and it had a radius of, let's use a different color, a radius of R, and we were located someplace on this line. And you were asked to find the electric field and the electric potential a distance z away from the center of the circle. That was the problem. Do you guys remember it? Whether you start with electric field or you start with electric potential, the issue is you're asked to find the electric field. So at some point or another, you need a method for finding the electric field. Do you remember the original method for finding the electric field that we learned at the very beginning of the year? And it was even before, well, I mean, it was Coulomb's law, but it was kind of before we knew what electric field was. We defined electric field by force. Right? So we'd find the force on a point charge placed at that location, and then from there, we would divide out by the point charge's value. And then from that, use that as our means of finding the electric field. That often led us to using something like Q over 4 pi epsilon naught r squared, because that is the result of Coulomb's law when you divide out for the point charge. And it's in the r direction. You have to remember this is a vector value. It takes its vector direction from the direction of the force on a positively charged particle. This only worked for point charges. So then we look at this object here, which is clearly not a point charge. And we say, well, how can we apply it to this particular example? Well, we didn't originally. Our original example, because there is this question. Well, there's lots of little pieces of charge. So how do we deal with it? Well, we look for symmetry. We look to see if every portion of the electric field is going to be in the same direction, or if there's going to be some in other directions. We have to look and see, is there some kind of symmetrical pattern happening here? But at the end of the day, the only way we're going to be able to find the electric field for this particular shape is to make a decision on how we attack the problem. There is symmetry here, not enough symmetry for us to be able to use Gauss's law, but enough symmetry for us to use geometry to only consider certain components of the electric field. That's why in this problem, I would have told you, okay, well, this is a single ring of charge. Break it up into small pieces and look at each piece. In a problem like this, to look at each piece suggests we're only going to get a piece of the electric field, right? A portion of the electric field for each piece. That is no different. We're saying that each piece has an amount of charge dq. And it doesn't matter what symbols we use here. These symbols are ours. They're transient. They're there to get us to the end. So you can do d capital Q, you can do d lowercase q. It doesn't matter. We are creating a transient variable that we're going to use in the pursuit of this problem. So if I say dq, and I put this over 4 pi epsilon naught r squared, I still have to deal with the direction of that vector. I still have to recognize that this is only a part of the electric field. It's at this point that we have to make some decisions about how we break it up and how we do this sum. But this will be a sum. We are going to add up every contribution to the electric field in the same, probably break this up into an infinite number of pieces. Right? We are taking a distribution of charge, and we're going to break it up into a lot of little pieces. Now, I know that that's a bit of a mind stretch for some of you, but it's not much different than saying, okay, there was one charge before, now there's 2 charges, now there's 3 charges. We're just going to have lots of charges. That's why we're coming up with something generic, something that we can say this represents every single charge, every possible location that dq can exist on this ring, which is why we have to kind of make some choices about where's the first of these dq's going to be and where's the second one. Can I find a way to geometrically represent where every single one of those charges is? I didn't have to do that on this here. That every single one of the charges is in a certain configuration. We can point to them all. We have to come up with a way to point to them. So I would tell you, say pick a part of your ring and mark it. Say that that is going to be your dq. And I generally chose the top or bottom, not because that's where I wanted to start or not because that's what I wanted to use, but because I was going to draw on this. And because I was going to draw on this and going to have to deal with the geometry of this, I wanted you to be able to see where the hypotenuse was and how the distance between this piece and our location in space were related. But I could have just as easily have said, well, this is where dq is over here. The problem is that I'm drawing this on a 2-dimensional board and it has extension. I can't draw the ring in a 3-dimensional way, at least not easily. I had told you, can you recognize that there's a certain amount of symmetry that we can use? That for this piece, there's another piece down here that's going to provide certain symmetrical benefits to our answer. Does this make sense to you so far? So we would say, okay, well, there's an R here, and there's an R here. And the idea is that along this line is DE for the piece on the bottom, and along this line is DE for the piece on top. But there's certain symmetry here, and I can exploit this symmetry for the problem. And what I mean by that is, well, I'm only going to concern myself with the part of the electric field down the center because of the symmetry that's here. But there's also a dq here, and probably a reciprocal dq over there. Now, all of this to say, we've done this problem several times already. I don't really feel like rehashing it all the way, but what I saw on Friday was you guys didn't understand what you were adding up. That's a foundational issue, which is why I think we need to see this a little bit more. A lot of these things don't change over this particular sum. And that's the other part that you need to start paying attention to, because I don't think that you really are. For example, this R, this is going to be the same for every single piece. The truth is, although R is not going to be in my answer, I'm not sure it's in my integral either. We would replace it early, but does R change as we go around the ring? The thing we are summing isn't our distance Z. A lot of you, when you think about the electric potential, think we're summing the distance Z in this expression for electric potential. Because if we were saying, what is the potential from infinity to this point, we might use this expression for that to figure out what the electric potential is from infinity to this point in space. That's reasonable. That sum is a different kind of sum. We're adding up how much work is done, taking a point charge from infinity and moving it lots of little dz's along the line. How much energy does it take to move it one tiny infinitesimal little change? That's a completely different problem. That is not what we are adding up in this question. In this question, we're adding up all the charge. We have to know what the sum is about. Does R, in this example, change when I move from this piece to this piece? No, it stays the same. It's not going to be part of my integral at all. It is a constant. There are some things that change. Not much, but there are some things that change. We should pay attention to those. But that's not one of them. In fact, if we look at all of this, I will have to add that we're going to do this, right? We're going to look for just the parts that are in the z direction because stuff in the y direction is going to cancel out. That's going to get added in over here, and it's at that moment that we realize we're only looking in the z direction, and that's going to be dq over 4 pi epsilon naught r squared cosine theta. Now, which of these things change when I go from this dq to that dq? Does the 4 change? Does the pi change? Does epsilon naught change? Does theta change? Does r change? None of those change. In fact, I could write this just a little bit differently and just put all the constants together. We okay so far? Now, ignore the problem for just a minute and look just at here. We want the total electric field, so we're going to integrate both sides. This is where I know I'm starting to reach the limits of your knowledge, but I'm not going to baby this anymore. You need to be paying attention here. I'm going to integrate both sides. That means I'm going to add up every single one of the dq's. That's what that says. So every infinitesimal piece, if I broke the ring up into a billion pieces, I'm adding up every little bit of electric field for all billion pieces. That's what I'm adding. But the only parts that matter are things that change when I move from one dq to another dq. Well, we just collected all the stuff that stays the same. None of those things change when I go from one dq to the next dq. So this side is going to be the electric field, the total. But none of these parts actually contribute in any meaningful way to the sum because they're in every single term. Just pull them all out. And I'm saying I am going to add up all the pieces until I get the whole charge. Truthfully, I could just say that this portion alone is just going to be Q. Right? It's going to be the entire charge. Because not one of those pieces, wherever it is on the ring, has any different contribution to the electric field. They all contribute the same equal amount. But yeah, I understand that. I never told you we could do it that way. I said we had to go, okay, well, dq is to a small bit of length as q is to the entire length. Right? I said something like that. And maybe I went further and said that maybe we should express this length as an arc length. Right? Maybe I would do that. Why? So that I could point to the first charge and make sure I had a geometric way to point to every single one of the charges. But we're still just adding it up. We're still just adding up each piece of charge. So when I take this and go, okay, so dq equals q over 2 pi r d theta. I just solved it for dq. And I want to add it all up by making a sum, starting at angle 0 and ending at angle 2 pi. What do you think you're going to get out of this? If we look at it, again, let's take out all the things that don't change. There's several things here that don't change. Does Q change as I go from one angle to another? No. Does 2 pi change as I go from one angle to another? No. And I can just go ahead and cancel out the two r's, right? Leaving with me the integral from 0 to 2 pi of d theta. Okay. There's no theta in this. So if I have to do the integral, what theta do I put in there? Theta to the 0 power. That's right. It's a polynomial. It's theta to the 0 power. We're just using the polynomial stuff here, the stuff that's all the voodoo that you learn in calculus. Right? Because remember, this process of doing the antiderivative and then plugging in your limits, that is the summing. That is adding up all the pieces. And I'm not here to explain to you why calculus does that. That's why you're taking calculus. I'll let Mr. Brashear and Ms. Smith explain that to you by making you learn the fundamental theorem of calculus and do the graphs. We break it all up and draw in the little rectangles. Who's had to do that already? It's fun, isn't it? All of that in service to show you that it just adds stuff up. That's all that is. In service to make you see that it's truly making a sum of all the pieces. I'm not going to do that. I'll let Mr. Brashear do that. It's boring. Almost as boring as this. But if I use the antiderivative of the polynomial function, I will get theta, right? Theta to the 1 power divided by 1, evaluated from 0 to 2 pi, which makes this q over 2 pi times 2 pi, which is q. I said to add up all the charge. I got the total charge. Why am I not surprised? Why did I have to do all of this? I didn't. I could have just gone right here and said if I add up all the charge, I could put q to the 0 power in there and make sure I evaluate from 0 to all the charges. You're just adding them up. None of the charges had a different effect on the electric field. All the charges had the same effect on the electric field. That's why this one is so easy. Now, I'm sorry to say this isn't the answer. Not because I don't want it to be, but because I can't have theta or r in my answer. I still have to put the geometry portions into this problem. The parts of the geometry that I'm allowed to put in there, they just didn't affect the answer. Which is why now I can say, okay, this has got to be qz over 4 pi epsilon naught times r squared plus z squared to the 3/2. Why? Because I can remember stuff from last week. And I've written down so many times what the cosine is on this problem and what the r is on this problem. Now, is that the way to do this question, to get the electric field? Sure, it's a way to do it. But what I saw out there was that you guys didn't know what you were adding. That's a problem. That's an issue. That's huge. That's the issue. Because then you had to find the electric potential. And if you do the electric potential for this problem, technically, based on what we've done here, your next choice is either to use the equation that has to deal with electric potential, or use Coulomb's law again for the electric potential. You could choose which of these two things to do. Now, which one did most of you guys choose? Well, I saw it. Most of you chose to use our definition for electric potential. This one. You didn't have to. But you had to pick something. So there is an alternative. But I'm going to pause for a minute. And I want to go electric field. One way to find it is to use the point charge formula. And when I say that, I mean either the electric field equals q over 4 pi epsilon naught r squared in the r hat direction, or a piece of the electric field is based on a piece of the charge. When does this work? Well, this works for collections of charges. That's one way it works. Or a distribution of charge. It would work for any distribution of charge if you can do the math on it. This will probably have the highest burden of math, though, because to use this formula means there will possibly be a sum that you will have to take. But this sum adds up the total charge. And I don't want to say just total charge, it's the total contribution to the electric field from each bit of charge. Now how you break that up, that matters. That was the whole point, is that it matters how you break it up. The ring of charge is the easiest of one of these to do. Quite simply the easiest, because every single point on that ring was the same distance away from point Z. We could modify the electric field. This is a way to do it. But there's another way to do it. And that way is about the electric potential. We can use the point charge formula for the electric potential. Why would I want to use that? Well, part of it is because the electric potential doesn't have a vector component. The electric potential is just a scalar value. So just like with the electric field, I can deal with point charges, just add them up. Or I can deal with a distribution of charges. It works for both. So this will handle point charges and distributions of charges. But this does not give me the electric field right out. This gives me the electric potential right out. To find the electric field, there will have to be another step. You get your expression for the electric potential, and then the electric field is the derivative of the potential. And I'm going to put ds here. Instead of x or y or z, I'm going to put s. It's a placeholder to indicate you're going to have to take the derivative, but you're going to have to choose where you take the derivative, in what direction. Let me be an x in that answer for the electric potential. So I wouldn't want to take the derivative with respect to x. So the s is a placeholder. Remind me that I can only do this in one dimension at a time. Now that might or might not be easier. You'll notice that you don't really save very much, do you? Going back over there, you have another way to find the electric field. A couple of them still. Gauss's law can find the electric field. It's also a different summation. It involves you finding the flux first, understanding that we're dealing with the Q enclosed and the total electric flux. And this will only work if the electric field is something that is constant or zero, or doesn't contribute to the flux. Right? Remember, this will only find the electric field if somehow you can work E out of your integral. That's the only way it'll find the electric field. So as a means of finding the electric field, this is going to be for only very narrow use cases. Generally, I used to say ones that were highly symmetrical, But that's not really what I mean. I mean cases where the electric field is constant over some portion of your area. Because you need to be able to tease this out of the integral. You need to make sure you have a situation in which the electric field isn't changing on different parts of your area. So when I look back at this complete three-dimensional surface, we could take the ring and turn it from what was quite an easy question to something that is not the same. What if we're talking about being on the same plane as the charged ring? So this is all on the same plane. Do you understand how this problem is substantially different now? In a way that it's hard. Is it outside of your capabilities? Might be. I don't know. Can you set this one up? Well, okay, we could start. All the things are going to be the same. All the things I'm asking you to do are going to be the same. Can you do this, though? For example, that part remains, that we're going to have to recognize what's the best way to find the electric field here. Well, I think the best way to find the electric field here would be probably not the method I'm about to use, because I think the method I'm about to use is going to be the hardest way to find the electric field here. But again, can you use the method we just did? Yep, it'll work. I'll need to pick a point on this to kind of get an idea for what a piece of the charge looks like. I do think there's some symmetry. I don't know if it's going to be as easy to exploit as it was before. Because now I'm looking at what R is going to be. And R is this distance. Right? So if I put R here and recognize this is DE, I do think there's a symmetrical piece on the bottom, don't you? Sure. Pretty sure, yeah. So I do think I'm going to be looking only at the part of the electric field that's this way. I do think that's going to be the case. But there's some geometry here. Let's consider. Let's start with our DE in the Z direction. We're going to stay going that this is the Z direction. First, it's going to be DQ up here. 4 pi epsilon naught r squared cosine theta. All of that's going to be there still, right? Where this is theta and that's r. But I think r is going to be a little bit harder now, don't you? We might need to come up with a way to figure out what r is. I know I have some things I can use, but I think the level of difficulty of this problem has just increased substantially. Right? I might need a placeholder here, a different angle, to kind of determine where I am on the ring. I think there might be a relationship between this angle and this angle, don't you? You might need to figure that out. You see, this problem isn't much different in setup than the other one, but it is different. When I start thinking about this and start thinking about all the different DQs, does theta change with each DQ? Yeah, it does. It's no longer a constant. Does R change with each DQ? Yeah. Does epsilon change with each DQ? No. Does pi change with each DQ? No. Does 4 change with each DQ? So when I go to look at this problem, suddenly I can pull all those constants out that aren't changing. But everything else now has something to do with which DQ we're at. This problem is going to be a sum still. I'm going to be adding up every DQ, all true. But every DQ contributes a different amount because every DQ is in a different direction, a different place, a different distance away. And although there's some symmetry, I think the top half of this ring and the bottom half of this ring are symmetrical. Finding r might be hard for you. Do you recognize, though, that finding r is a geometry problem? That there's a geometry about it that we could work out? And is it true that probably finding theta is also a geometry problem? Now, this question's hard, kind of. You do see a triangle in there, though, don't you? A triangle that's probably related to this angle and this r. Do you see that? And that once you realize that this r and this theta can probably be put in terms of this r and this phi. Do you see that? You'll probably also need something like this distance. Well, that's just z, isn't it? I'm pretty sure this answer is going to end up with z in it, because I think where I am along z is going to change the answer. And this still better produce an answer where when z is 0, the electric field is 0. So it just puts us back in the center of the ring, doesn't it? And when z goes to infinity, the electric field goes to infinity, because it's going to put us way far away from the ring. Those two things are probably going to be the same, but I think what happens in the middle, that's probably going to be different. Again, not going to work this problem out. I think you should. But I think this is now a geometry question. I do think at the end of the day, I'm going to do a sum. And what I'm expecting is that sum is probably going to be something like add up every contribution for phi equals 0 to pi, and then double it, because there's two sides, right? Because I can point to the first piece of charge when phi is 0, and the last piece of charge on the back end of the ring when phi is pi, and then double the answer. None of that is calculus yet, mind you. Everything I'm talking about here is still geometry. I'm just talking about where I think that first piece is going to be and where I think that last piece is going to be. Here, I would probably want to take the derivative with respect to dz, since I'm looking for the electric field along z. I probably wouldn't want it along a different direction, a different dimension that isn't that direction. So I want to use a useful derivative that has to do with probably the problem. In this case, we were looking for an expression for the electric field that has z in it. So I'm going to take the derivative with respect to dz. All the same things, except now it's going to be dv equals, there's no ez here. It's just going to be dq over 4 pi epsilon naught r. I am still going to have to find an expression for r that's probably going to be based on phi and probably based on r. But I don't have to find another expression for theta. I only have to find an expression for r. I don't think that's still going to be easy. I still think that's going to be trouble. But it's easier than finding one for each. I'm still going to have to figure out where the first piece is. I'm still going to have to figure out where the last piece is. And I'm still going to have to make a summation of all of it. And again, still the same kind of idea. I don't think Gauss's law works here. I don't think there's any three-dimensional shape I can put around this where the electric field will be the same everywhere that will give me z as my vector of choice. There might be a shape, some kind of weird donut thing maybe, where the electric field is constant everywhere. I have no idea. There might be. I'm not even going to bother to look. Because what I'm saying is I don't think that shape is something that I can integrate. Right? When we talked about shapes that we can integrate, we're talking about looked different. It was arguably the exact same question, but I don't know that you guys recognized that it was the exact same question. If I just replace D with an R here and say that this is Q and this is Q, and I ask for you to find the electric field here, a perpendicular distance away from the plane that holds these two charges. This is the same question. It's asking you to do the same things. Now, the answer here will be different here, right? I have twice as much charge in this example than I have. This question tells you, or at least it informs how you took this one as a fairly standard practice question. It was true that you had to work out a few things. Like you had to come up with a way of dealing with how far apart they were. Even though they were given fairly straightforward instructions, we didn't get this value for R. We had to come up with this value for R. And we did so by doing a little bit of trig or geometry. That seems to be something that happens for a lot of these problems. And then we also had to recognize that there was a portion of the electric field that was off axis, right? This is the direction of the electric field, but we're going to have a counterpoint to this particular direction for the electric field because there's another charge over here. And so we worked on the idea that there was a certain amount of symmetry in these problems that we could use to exploit to simplify it. But our true answer is to say that, well, there's going to be an electric field potentially in the x direction. Well, I guess z direction would be better for this problem. Z direction and an electric field in the y direction. But it's in the y direction that the electric field cancels out because there's a part of the electric field in the y direction this way and part of the electric field in the y direction that way. We stopped worrying about those because there's a certain amount of symmetry. Now, I bring this problem up specifically because it did involve us having to find some portion of the electric field along the center. And it was that portion, this part here, that we focused on. And we would say something like, well, this is going to be E times the cosine of what that angle is. But again, we had to get rid of the angle. I'm building this up because this still, at the very end, when all of it was done, for E, we were going to use Q over 4 pi epsilon naught R squared. And we're probably going to have two of these. One for each particle, and then we would add them up. Well, how does that inform this? This is piece number 1, and this is piece number 2, and we're adding them up to get the total. We added up every contribution to the point charges and how they contributed to the electric field. One of the charges is above the line, one of the charges is below the line. I'm telling you here that there's only two charges, and they're very clearly marked. But I'm